Okay, hello and welcome to another Cambridge National Award Certificate in Systems and Control Engineering R113 Electronic Principles. So another revision session for the exam, which will be on Monday. So we've been working our way through this paper and looking at some of the sort of questions that come up and looking at basic theory that sort of underpins these questions, things that you need to understand. Now earlier we looked at this problem where we looked at putting in a limiting resistor to protect an LED, and it was about sharing the voltage, and it's that sharing of the voltage that I want to get into in a little bit more detail, looking at another question which is something like this, where we've got two resistors in a series, but actually we've got an output coming out from between them, and this arrangement is known as a potential divider, because the voltage will be divided between the two resistors. So we need to look at some of the values to see how this actually functions. So we'll come back to that question. What I want to do first is to try and sort of simplify that a little bit. And so let's just have a look at how voltage is divided. So I'm going to draw a little circuit, two resistors, and then an output coming from this point here, and I'm going to put 12 volts in here, and I'm going to have two resistors that are of equal value, 100 ohms. Now when we're looking at potential dividers, we'd normally measure the voltage across here, so we're looking at the voltage across this resistor, the potential drop across this resistor. So let's first have a look at the whole circuit. So we've got 12 volts in total, we've got 200 ohms in total, and we'll have an appropriate current using VI and R. So we can just have a reminder of Ohm's law and look at the situation that we've got. So we've got voltage divided by will give us the current, voltage divided by resistance gives the current. 2 into 12 goes 6, and we've got two noughts there, so we're going to have a number of decimal places. 0.06, we've got two noughts, two decimal places, so we've got 0.06 amps there in that circuit. Now the formula for this voltage, the voltage output, is V out is equal to, this is R2, this is R1, and it's R2 divided by R1 plus R2, or the total, and then you times that voltage in. This is the voltage in here. Okay, so if we look at that, we're going to end up with, well, R2 is 100 divided by 200 . So R2 100, R1 plus R2, 100 plus 100 is 200. That gives us, well, basically as a fraction, it's a half times the voltage in, which was 12 volts, so we've got a half times 12 volts equals 6 volts. So here we would have 6 volts. Effectively, the potential is being divided. It's been divided in this case in half, and it's a situation where this equation gives you a ratio, gives you a fraction that you multiply the voltage that goes in, and it gives you the voltage that comes out. Just have a look at another example, and this time we'll change the voltage. We'll change the bottom resistor R2, and we'll make that one 200. So we've got 100 here and 200 here. So if we measure the voltage across here, we'd have the voltage out is equal to R2, 200, divided by, now we've got 300. So effectively we've got 2/3 times the 12 volts. So 2/3 of 12 volts, a third of a volt is 4 volts, so 2/3 would be 8 volts. So we'd have 8 volts across this resistor, which means we'd have 4 volts across this resistor. 8, 9, 10, 11, 12 volts in total, because there's always 12 down to 0, as we've discussed before. So the voltage has been divided and shared in a ratio relevant to the value of the resistors, using voltage out, R2, divided by R1 plus R2 times the voltage in. So let's look now at how that's being applied, how that can be applied. If we look back at our question, we've got our temperature sensor. This is a temperature sensor line with a little dash through it. It's got -T on here in degrees, and this is a thermistor. I don't want to look at that one yet. I'll look at this question last. I want to look at this idea of some sort of sensor that's responding to our environment. So let's have a look at an example which is a little bit more quick in its response. Temperatures sort of can be a little bit slow. So I'm going to put my 100 ohm resistor here, and then here I'm going to put a light dependent resistor. There's the light coming in. So now when the light's shining on a light dependent resistor, the light gives the electrons energy, so it makes it easy for the electrons to flow. That's how an LDR works. The light makes it easy for the electrons to flow. So this has very low resistance, so we could say, just for the sake of argument, we'll say that it has 50 ohms, and therefore the voltage across that light dependent resistor would be 50 divided by 150, R2 50, R1 plus R2, R1 and R2 150 times the voltage in. So we've got our 12 volts here. We would end up with, well, let's look at that. That's a third, isn't it? One of those and three of those. So a third of 12 volts would be 4 volts. Right. So now let's have a cloud comes in. There's our cloud. Now there's no solar energy, so the electrons are now going to really struggle to get through here. This becomes quite resistant. In fact, let's say it comes to 300 ohms. And now if we look at the same situation, we've now got 300 divided by, well, I've got 100 plus 300 is 400 times our 12 volts. So again, cancelling down, that gives us 3/4 times the 12 volts. So now we'll have, well, 1/4 would be 3 volts, and we've got 3 of those, so we would have 9 volts. So see the difference? The sensor with light shining on it, there was a voltage of 4 volts, but as it became dark, the voltage at this point, or across these points here, went from 4 volts to 9 volts. So in fact this circuit was reacting to light. It is basically a sensor. So the potential divider circuit with Vout equal to R2 divided by R1 plus R2 times the voltage in. This is really people often forget this, it's very important you remember to times by the voltage in, gives us, with a particular type of component, like dependent resistors or thermistors or moisture detectors, gives us the ability to sense the outside world and feed that into a circuit so that a circuit can respond. Now the question didn't actually ask for a calculation. This question is asking us about why you'd have a variable resistor here. But before you could answer this question, you would need to understand that this was a potential divider and that the voltage would vary depending on the values of these two resistors. So if you think about it now, this temperature, a set temperature, would give you a set voltage across this point, and it would change the value of the voltage across this point, so the output here would change. But this is a variable resistor, so what we can do is increase and decrease this resistance, which would give us the opportunity to fine-tune, and there's a key word here, calibrate. It would be able to calibrate this circuit so it worked on a particular temperature. But let's have a look at that then. And again, it gives us a chance to look at how thermistors work. So here's the circuit. So a thermistor is a line with a line through it, and they've marked theirs with T minus 0, T degrees. And then we've got a variable resistor. There are a number of ways of indicating a variable resistor. That means variable as well, so you can just put a line through it as a variable resistor. And there's going to be our V out. We'll put 12 volts in, because I like working with 12 volts. So we can sort of study how this circuit works then. So this is described in the question as an NTC, which is a negative coefficient, a negative temperature coefficient. Basically this operates on a graph that looks a bit like this, where resistance goes like so. So you'd have 0 to, let's say, 100k, and the temperature goes along the bottom, say 0 to 100. And basically what happens in a resistor like this is when the temperature is low, the resistance is high. So 0 degrees, you've got a high resistance. And as the temperature increases, its resistance drops. And it's quite predictable. It is in a curve though. Okay, there'll always be a little bit of resistance. So low temperature, high resistance, high temperature, low resistance. Right, so that's how this is going to react. And this is a variable resistor, so basically, you've seen those little blue things where you twist them, sometimes called a potentiometer, but a variable resistor can work in a range and you can fine tune it. So let's say we start off with a temperature that's giving us 100 ohms, and we set our variable resistor to 100 ohms. Well, in that situation, we've got exactly this. We've got what we had before. Yeah, so we know what the answer to that's going to be. We would be able to have, across there, 6 volts. Now, let's imagine that it's going to get cooler. Okay, so let's imagine that it's a chilly day and we're going to have 200 resistance. So the temperature's dropped, the temperature's gone this way, and so the resistance has gone up a little bit. Well, we would do our equation, R2 divided by, so now we have a third of 12 volts, which would be 3 volts. So we had 6 volts here on temperature 1, but now we've got 3 volts So as the temperature has decreased, so has the voltage. So this circuit is responding. Now it might be a case I might think to myself, well, you know what, this is the temperature, this is a comfortable temperature, I don't want anything to happen here, so I want to keep this at 6 volts. So what I'd have to do then is I could adjust this to 200, and now I would have a balance again. I would get 6 volts here and 6 volts here. Or I might say, well, I want something to actually happen. I want something to trigger at 9 volts, so I could increase this to a value, so I could make it 300 or 400 or 500. I could change the value to change the operation of the circuit, and like I said, the word we were looking for is calibration. So hopefully that's been useful. Hopefully you can understand now that's how a potential divider works. So it creates a fraction using this formula, which you do need to learn, and it can be applied in a number of circuits specifically to do with sensors. And how that works is where we're going to go next, because this voltage out very often goes into the next very important component we're going to look at, which I'm going to sketch here. And I'm going to leave that for you to research before the next video. What is that component and how does it work?